Okay, so in this video, we're going to go over chapter 3.2 from our textbook, which goes over derivatives of exponential and log functions. So first we'll look at the derivative of e to the x. And so from here all the way down to here is just a proof of finding the derivative of e to the power, or e to x. And you can look at it in more depth in your textbook, but I just wanted to put it here to illustrate that we can do this four-step process, which includes finding the limit of our difference quotient as h goes to 0 in order to show that the derivative of e to the x is just e to the x. So the derivative of the exponential function is just the exponential function. So what we'll do is go over a few examples using this new definition. So looking at a here, we want to find the derivative of f of x, so f prime of x. So this first term here, we have 4 times e to the power x. And something to remember here is from chapter, I believe, 2.5. If we want to find the derivative of this whole thing, we can just find the derivatives of all of these individual terms. And then we also have our constant multiple rule, which says if we have a constant multiplying our function here, we can just leave it out front. So we'll have 4 times the derivative of e to the x. E to the x. And so we know the derivative of e to the x is just e to the x. All right, now we want to find the derivative of 8 times x squared. And remember our constant multiple rule, we can just leave 8 there. And then we'll use our power rule to find the derivative of x squared. So we know that we'll bring 2 down in front, and then we'll get x to the power 2 minus 1, which is just 1, so we just have an x there. And then for 7x, our 7 stays out front. And then we'll have x to the power 1 minus 1, which is 0, so we just get 7 out front. And then we know the derivative of a constant will just be 0. Right. So then we have 4 e to the x plus 8 times 2, so 16x plus 7. Right, so that is the derivative of this guy. Now let's look at b. All right, so again, we can just find the derivatives of all of these terms individually. So for this guy, we'll do the power rule. So 7 comes down in front, and then we have x to the power 7 minus 1, which is just 6. Doing the same thing for x to the 5th power, we'll bring 5 down in front, and then we have x to the 5 minus 1, which is 4. Now something to be careful with here is we have e to the power, to the 3rd power. So remember, e is just a number. It's roughly 2.71828. So e cubed is just going to be 2.71828 cubed, which is just a number. So this tells us that this is just a constant. So be careful with that, because we know that the derivative of a constant is just 0. And so I'll write this in red too, so we can keep track of that. All right, then we have minus derivative of x, that's just going to be 1. And then the derivative of e to the x, which we know is just e to the x. All right, so then we get 7x to the 6th power minus 5x minus 1 plus e to the x. And so this is our derivative for f of x in part B. So something to note here is that when we're dealing with e to the x, we're not going to be using our power rule to differentiate it. So we already saw above that the derivative of e to the x is just e to the x, but just want to reiterate that we're not bringing x down in front and then taking e to the power x minus 1. And This rule, the power rule, only works in certain exponential forms. So in the form of x to the n, where n is some constant, and the base here, x, is a variable. So that's also why we're not using the power rule to find this derivative either. Our base is exponential, and our power is a constant, but this as a whole is just a constant. All right. Now we're going to look at the derivative of the natural log. So below and this here are just some important facts that we saw from section 1.6 on log functions. So just putting this information here, we're going to bring some of this back. Okay. Also, here is the four-step process for finding the derivative of our function ln x. So again, we can do this four-step process by taking the limit of our difference quotient as h goes to 0. And when doing so, we find that the derivative of our natural log function is 1 over x. All right, so we'll use this to go through some examples. So let's look at A here. Y is equal to 10x cubed minus 100 times ln x. So we're trying to find y prime. So here we'll use our constant multiple property, so 10 stays out front. Then we're going to multiply that by 3, so we're bringing the 3 down in front using the power rule. Then x to the power 3 minus 1, which is 2. Then again, using our constant multiple property, this constant, 100, is going to stay out in front. And then we want to look at the derivative of ln x. And then up here, we know that that is 1 over x. All right. So simplifying this a little bit, we have 30x squared minus 100 over x. So that is our derivative for part A. Now looking at part B, the first thing I'm going to do is rewrite this, our function y, using first the log property that we saw in section 1.6, which said that if we have ln m to the power p, that's the same thing as bringing p down in front and multiplying that by ln m. So that means this term here, this ln times x to the power 5, can be written as 5 times ln x. Then we have this plus e to the x. And then something else to remember is that ln and e are inverse functions. So these guys will cancel. And then this 2 will come down, so we're just left with 2 there. Okay, so I just wanted to rewrite y like that so it's a little clearer what's going on. So we have our 5, our constant multiple, out in front, so we keep that there. And we want to find the derivative of ln x. Well, we know that's just 1 over x. So that's the derivative for that term. And then we know the derivative of e to the x is just e to the x. And the derivative of a constant is 0. So then we get 5 over x plus e to the x. All right. So now we're going to look at other log and exponential functions. So we talked about this before, I believe, but the number e is the most preferred and common base that we'll use. But in some situations, it's convenient to use a base other than e. And so the derivatives of y is equal to log base b of x and y is equal to b to the x can be obtained by expressing these functions in terms of the natural log and exponential functions. So the first thing we want to do is find this derivative. So we're going to try to find a relationship between log base b of x and ln x for any base b such that b is greater than 0 and b is not equal to 1 in order to do this. So we'll start with y is equal to log base b of x. Well, we know that if we take this to base b on both sides, these guys will cancel. We saw this in chapter 1.6. So we get b to the power y is equal to x. All right. Then if we take the natural log on both sides, we get ln b to the power y is equal to ln x. Using our property that this power can come down in front, we get y ln b is equal to ln x. And then solving for y, so dividing by ln b on both sides, we get y is equal to ln x over ln b. All right. So this implies that since y is equal to log base b of x, that's what we started with here, and we just found that y is equal to ln of x over ln of b, this tells me that these two guys are equal. So log base b of x is equal to, and I'll write this as 1 over ln b times ln x. That's how it's written in the book. So this is called the change of base formula for logs, and finding this relationship between using log base b of x is how we determine that. And so this is called our change in base formula. All right, then we differentiate both sides of this guy. So taking the derivative of log base b of x with respect to x, we have this 1 over ln b out in front, because this guy here, actually I'll highlight it this way, this 1 over ln b is just a constant. So we take it out in front and then just find the derivative of ln x. So this 1 over ln b stays out in front, and we know from before that the derivative of ln x is 1 over x. Okay? So that's why we wanted to find this change of base formula, so that we could determine the derivative of log base b of x. Now, doing the same process, we can find a relationship between b to the power x and e to the x for any base b where b is greater than 0 and not equal to 1. So doing the same thing here, essentially, we have y is equal to b to the x, and then taking natural log on both sides so we can use the power rule for logs, brings this x down in front, and then solving for y, we get y is equal to this. Right? And then since y is equal to b to the x and y is equal to this, that means these two guys are equal. And so this is our change of base formula for exponential functions. All right. Now, something to note here, it can be shown that the derivative of the function e to the c times x, where c is just some constant, is equal to this here, and we'll go into more depth on this in section 3.4, but for now we're just going to take that as a fact. When we differentiate both sides of this equation here, so we're going to take the derivative of b to the x, we find that is equal to e to this power here times ln b, because ln b is our constant. So using this fact up here, we can think of ln b as our c in this case. Okay. So then this tells us that the derivative of b to the x is going to be b to the x times ln b. All right, and that information that we just went over is written here. So the derivatives of our exponential and our log functions. So again, we saw the derivative of e to the x is e to the x. And then we just showed that the derivative of b to the x is going to be b to the x times ln b. Similarly, we saw already that the derivative of ln x is 1 over x. And then we just showed up here using our change of base formula that the derivative of log base b x is equal to 1 over ln b times 1 over x. All right, so we'll use that information to go over this example here. So we want to find g prime of x for these functions here, a and b. First, looking at a, we'll find the derivative of x to the power 10. This one's pretty simple. We're just going to use the power rule. So 10 comes down in front, and then we have x to the power 10 minus 1, so x power 9. Then we want to find the derivative of 10 to the x power. So that is the same as this guy here. Remember, b is just going to be some constant, and it's to the x power. So 10 to the x, the derivative of that is just going to be 10 to the x times ln of 10. Just using the derivative of b to the x here. In this case, b is 10. All right, so that's it for that one. That is our derivative of g of x there. Now doing the same thing for b. First, we want to find the derivative of log base 2 of x. So we will use this guy here. In this case, our b is 2. So the derivative of log base 2 of x is going to be 1 over ln of 2 times 1 over x. Then we'll do the same thing for this guy here. First, remembering that we just have this constant 6 out in front. Then we want to find the derivative of log base 5 of x. So again, using this property here, we get 1 over ln of 5 times 1 over x. All right. Simplifying this a little bit, we get 1 over ln 2 times 1 over x minus 6 over ln of 5 times 1 over x. All right, and that is our derivative for that guy. Okay, so let's see how we can use this in some real world examples. We're going to look at a price demand model. And so we're told that the store in example 4, so just some store, you can look at the example in the book, but it sells reversible fleece blankets. And we're told that if the price demand equation for a reversible fleece blanket is given by P here, so that is for X blankets sold at a price of P dollars per blanket. Okay, and what we want to do is find the rate of change of price with respect to the demand when the demand is 400 blankets, and then interpret what this means. So we already know, since we're trying to find the rate of change, that we want to find the derivative of our price demand function. So let's first find P prime. So we have this constant out in front, so we'll keep that there. We have 200, and then we want to find the derivative of 0.998 to the x power. And remember, by the definition of the derivative of b to the x, we're going to get b to the x times ln b. And in this case, our b here is 0.998. So we'll have 0.998 to the x times ln of 0.998. All right. So that's it. That's going to be our derivative for p here. And then the question is to find the rate of change of price with respect to demand when the demand is 400 blankets. So we want to find the rate of change when the number of blankets is 400, because this price is going to be the rate of change of this price is dependent on X on our number of blankets. So all we have to do is plug in X into this equation here. And then plugging this into a calculator, get roughly negative 0.1797. So this is going to be about minus 18 cents. So what this means is when the demand is 400 blankets, the price is going to decrease by 18 cents per blanket. All right. Now, the last example we're going to look at is one with continuous compound interest. So we're told that an investment of $5,000 earns interest at an annual rate of 6% and it's compounded continuously. And so we want to find the instantaneous rate of change of the amount in the account after 3 years. So we know that we're dealing with continuous compound interest. So our amount is going to be represented by that guy there. And so after T years, our amount is going to be our principal, which was 5,000, times e to the power of our rate, which is 6%, times t. Now the question asks for the instantaneous rate of change, so we're going to be looking at the derivative. And something to note here, e to the power 0.06 is just a constant. So we're going to let that equal b, and you'll see why in a moment. So we're rewriting our amount as 5,000 times b to the power t. And the reason why is when we want to find the derivative or our instantaneous rate of change of our amount, we'll use the fact that the derivative of b to the x is b to the x times ln b. So we get this 5,000 out front times b to the t times ln of b. Now plugging our value for b back in, we get 5,000 times e to 0.06 times t times ln of e to 0.06. All right, and then remember ln and e are inverses, so that guy cancels. So we get 5,000 times e to 0.06 times t times 0.06. Then 5,000 times 0.06 is equal to 300. So we're left with this. All right, so that would be the instantaneous rate of change of the amount. But we were asked of this change, or what this change would be after 3 years. So what we'll do is we'll plug in 3 for t, and so we get 300 times e to the power 0.06 times 3. And then plugging this into a calculator, you get roughly $359.17. All right. So the last thing we're going to look at is part B of this question. So we want to find the instantaneous rate of change of the amount in the account at the time the amount is equal to $8,000. So we're looking at the instantaneous rate of change again. So let's take a look at what that is. We found that that would be equal to so before simplifying this to get 300, we have 0.06 times this guy here. And if you remember our original equation for our amount, it's equal to 5,000 times e to the power 0.06 times t. And that's exactly what we have here. So I'm going to replace this with our amount. So this tells us that our instantaneous rate of change is always going to be 6% of our amount, A of t. Alright. Now this makes part B much easier because we're asked for the instantaneous rate of change of the amount in the account when the amount is equal to 8,000. So we're given our value for A of t. And so the instantaneous rate of change when A of t is equal to 8,000 is just going to be 8,000 times 0.06, which is equal to $480. Alright, so that is going to be it for this video.